Hello, my name is Oliver. I'm the maintainer of the OpenLogic FPGA standard library. If it comes to reliable FPGA design, clock domain crossings are omnipresent. In today's video, we're going to discuss what clock domain crossings are available in OpenLogic, how they are implemented, what their pros and cons are, and how you can choose which one best fits your application. The video is really about the implementation of clock crossings in OpenLogic and not so much about the theoretical background. Of course, we will cover one or the other of these theoretical background topics, but we will not dive deep. If you are interested in the theory behind clock crossings, I will link two resources. One is an article series from Lukas Vik, and the other one is a presentation from Amr Adel. Let's first discuss how you can find out what clock crossings are available. You just navigate to the main page of OpenLogic on GitHub, look into the README and select the entity list. There you scroll to the section Clock Crossings, which is in the base area of OpenLogic, and all the clock crossings are listed. We will go through them in this video one by one. The entity names for all clock domain crossings start with CC for clock crossings, so you can find them easily, except for the asynchronous FIFO, which is categorized as FIFO. All the clock crossings also come with synthesis attributes to ensure optimal synthesis with all the tools supported. There is also a link to the clock domain crossing principles, which documents concepts that apply to all clock crossings. Let's first have a look at the AllCDC bits. This entity implements a clock crossing for individual bits. The implementation is relatively straightforward. The data is latched on the source clock domain and synchronized using a standard double-stage synchronizer on the destination domain. The figure depicts a two-stage synchronizer, but the number of synchronization stages can be configured. Normally 2 stages are fine, but for applications with very high MTBF requirements, you may want to have more synchronization stages. This clock crossing does guarantee that there is no metastability on the destination clock domain. However, it does not guarantee that all the bits arrive in the same clock cycle. Individual bits may arrive one clock cycle earlier or later, which is the reason why this clock crossing should not be used for multi-bit data. You may ask yourself why there is a flip-flop required on the source clock domain. Let's look into that topic as well. For a two-stage synchronizer to work correctly, it is crucial that there is no logic between the last flip-flop on the source clock domain and the first flip-flop on the destination clock domain. For example, if there would be an XOR between the two and the skew is not balanced, it could happen that a pulse is detected, although this logically would not be expected. Including the flip-flop on the source clock domain into the component ensures that no logic can be added by the user between the two clock domains. The interface of the component is straightforward. There are clock and reset on both clock domains, plus the data input and output. Note that the reset is synchronous. All resets in OpenLogic are synchronous, and this applies to clock crossings as well. Regarding generics, the number of bits to be clock crossed can be configured, so the same clock crossing can handle more than one bit. You can also find a generic to configure the number of synchronization stages on the destination clock domain. This generic you can find in all clock crossings in OpenLogic, so for all clock crossings the number of synchronization stages is configurable. Next we look into the Allbase CC Pulse, which does transfer pulses from one clock domain to the other. Again, the architecture is very simple. Pulses are converted into a signal that toggles once for every pulse, which is then clock crossed using Allbase CC bits and converted back into pulses on the destination clock domain. This structure works well as long as the pulse rate is significantly lower than the clock speed of the slower clock. And again, this structure does not ensure that all the pulses arrive in the same clock cycle on the destination domain. So it should be used for individual pulses only. Configuration-wise, the number of pulses to clock cross and again the number of sync stages can be configured. When looking at the interface, most things are as expected, but the reset output may catch your eye. The reason for that is that the structure only works safely if both sides are reset at the same time. Therefore, the clock crossing includes also a reset clock crossing. And the outputs here are the outputs of this reset clock crossing. That's a strategy you will find across most clock crossings in OpenLogic. These are outputs, so if you don't see any use for them, just leave them unconnected. This brings us to the reset clock crossing Allbase CC reset. This structure is a bit more complicated. First, the reset is latched on the source clock domain. The reset is then transferred to the destination clock domain using an ordinary reset synchronizer. The reset output is asserted asynchronously, so it can be used to reset outputs even if no clock is present. Removal of the reset is synchronous to stay in line with the synchronous reset concept of OpenLogic. Once the reset is detected on the destination clock domain, this is signaled back to the source clock domain using an acknowledge signal which is clock crossed using AllCDC bits. Only once this acknowledge is received, the reset latch flip-flop is cleared. The very same structure is applied in both directions, so this clock crossing is bidirectional. This structure ensures that every reset request on any of the two clock domains, even if it's only one clock cycle short, leads to a reset output on both clock domains, which is high for at least one clock cycle at the same time. The interface does not bring much surprises. As mentioned before, most OpenLogic clock crossings include a reset clock crossing, so whenever you see a reset output, this is the output of the reset clock crossing. As a rule of thumb, leave these outputs unconnected if your user logic does only react on the local reset. If your user logic reacts on the reset of the other clock domain as well, connect all reset requests to the reset inputs of clock crossings and reset your user logic with the reset output. If you use multiple OpenLogic clock crossings in parallel, it's sufficient to connect your user logic reset to the output of only one of those. Next, we will look into the Allbase CC Simple, which does transfer data together with a valid handshaking signal from one clock domain to the other. The data is simply latched on the source clock domain. The valid pulse is then sent to the other clock domain using Allbase CC Pulse, and on this destination clock domain, the data is latched when the valid pulse arrives, and both are output. It's obvious that this structure only works if the data rate is significantly lower than the speed of the slower clock. In contrast to the Allbase CC bits, this entity ensures that all data bits signaled together with the valid signal are consistent. As you might have noticed, OpenLogic clock crossings are built very hierarchically, so they use each other. This helps to reduce code duplication and duplication of synthesis attributes to ensure correct implementation. The interface is relatively similar to the interfaces shown before, just that data is now transferred to the other clock domain together with a valid handshaking signal, which is present on the input clock domain as well as on the output clock domain. Again, data width as well as the number of synchronization stages are configurable. Allbase CC Simple only includes the valid handshaking signal. If you also require the ready handshaking signal, so back pressure, then you can use the Allbase CC HandCheck. The entity is based on Allbase CC Simple, but it contains additional logic to ensure that data is accepted on the source clock domain only once the last sample is consumed on the destination clock domain. As you might have expected, the interface now contains full handshaking signals on both clock domains. The width and sync stages generics should already be familiar to you, so we only discussed the ready reset stage generic. For implementation reasons, you will achieve best timing if you allow ready on the input clock domain to be high during the reset. If you cannot accept this, set the generic to 0. If you want to make sure that upstream processing blocks on the input clock domain are not blocked by back pressure when the output clock domain is in reset, leave this generic on a value of 1. The next entity we cover is the Allbase FIFO async, because this asynchronous FIFO is very similar to the handshaked clock crossing from a clock crossing perspective. It also implements a fully handshaked clock crossing, just with more throughput. It can transfer one sample per clock cycle of the slower clock. The implementation is pretty standard for an asynchronous FIFO. It calculates read and write pointers on the corresponding clock domains and exchanges this data as gray-coded values. The gray coding allows using a simple Allbase CC bits to transfer the data at low latencies. For obvious reasons, the FIFO needs RAM. At the first glance, you probably may think this is resource hungry. However, for any technologies that provide distributed RAMs, meaning you can use lots as RAMs, an asynchronous FIFO implementation very often is same in size to the handshake clock crossing or even smaller. So as a rule of thumb, if you are targeting a technology that allows distributed RAM, you should prefer the asynchronous FIFO over the HandCheck clock crossing, and only use the HandCheck clock crossing in cases where you target the technology that does not allow distributed RAM. Why do we need gray coding here? Well, if you would exchange the pointers as normal binary counters, multiple bits would toggle in the same clock cycle. As you remember, the AllCDC bits does not guarantee that all bits arrive in the same clock cycle. As a result, we could see wrong data on the destination clock domain if multiple bits toggle. In the best case, just the last counter value would be visible, which would still be acceptable. But it could also be that other values, for example some in the future or some far in the past, are seen on the destination clock domain, which of course doesn't work. Gray coding ensures that from one counter value to the next, only one bit toggles. So worst case, we see the last counter value and not something else. However, this concept only works if the wraparound of the counter is at the power of 2. Otherwise, we would have multiple bits toggling around the wraparound, which would be unsafe. For exactly the same reasons as binary counters being unsafe, multiple bits toggle. Therefore, the asynchronous FIFO comes with the limitation that the depth of the FIFO must be a power of 2. Looking at the interface, this is unsurprisingly exactly the same interface as the HandCheck clock crossing, just with some additional signals regarding the FIFO functionality. Most generics are related to the FIFO functionality. Only the sync stages are clock crossing related. And as discussed, you can see that the depth of the FIFO must be a power of 2. If you choose other values, an assertion will be raised. The next entity we discuss is the Allbase CC status. As the name suggests, this clock crossing allows to exchange status informations between two clocks. It does so without knowing anything about the relationship between the clocks, for example which clock is faster and which one is slower, and it also does not require any handshaking signals. The concept of this clock crossing is relatively simple. Data is transmitted from the source clock domain to the destination clock domain together with a valid pulse. The pulse is then transferred back to the source clock domain using an Allbase CC Pulse, and continues cycling every time carrying data with it when it moves from the source clock domain to the destination clock domain. This concept guarantees consistency of the data. Any data showing up in the destination clock domain was valid in the same clock cycle in the source clock domain. On the other hand, we don't have any control of the timing. We know that data is transferred every now and then, so every few clock cycles, but we can't say exactly in which clock cycle of the source clock domain the data was latched. As mentioned, the interface is super simple and does not contain any handshaking signals. And generics are limited to the ones you already know from the other clock crossings. The last category we cover are the synchronous clock crossings. Those allow transferring data between two phase-locked clocks running at an integer frequency ratio. This situation occurs, for example, if both clocks are generated from the same PLL but have different frequencies. In this situation, static timing analysis knows the minimum time between two clock edges, and hence the timing can be analyzed by the tools. The clock crossing in this case only is responsible for handling the timing. The clock crossings ensure that no data is duplicated or dropped, and they also correctly propagate back pressure from the destination clock domain to the source clock domain. As you might expect, the interface contains fully handshake data, including valid and ready signals on both clock domains. Because no synchronizers are required in this case, we also don't have any sync stages generic, and we can only configure the width of the data bus. We now discuss the total of 9 clock crossings, each one having its pros and cons. To give some guidance which clock crossing to be used in which situation, I assembled a little table summarizing all the pros and cons of the different clock crossings. For every clock crossing, it shows whether it allows transferring data between asynchronous clocks, whether it allows to only pass sideband information or also data, if it ensures consistency between multiple data bits so that they arrive in the same clock cycle, if it contains a valid signal, so forward handshaking, if it contains a ready signal, so backward handshaking or back pressure, if it includes a reset crossing, if it allows to transfer data at full performance, meaning like one sample per clock cycle of the slower clock, and whether it requires RAM or not. You probably want to stop the video here and study the table in more detail. Correct functionality of clock domain crossings, as you might know, is tightly bound to timing constraints. All clock crossings in OpenLogic assume that delays from one clock domain to the other are constrained to be less than one period of the slower clock, which can be achieved by the timing constraints shown on this slide. In most tools, you as a user are responsible for setting these constraints. Only AMD Vivado is a nice exception in that regard. Vivado allows so-called scoped constraints. Corresponding tickle files are provided along with the VHDL sources. The easiest way to include the constraints is to integrate OpenLogic in Vivado as described in the how-to document. A script is provided which allows you to integrate all OpenLogic sources, including the corresponding constraints, into your project. If you do so, all clock crossing paths are constrained automatically, and really only the clock crossing paths. So if you have connections between clock domains outside of OpenLogic clock crossings, those still can be constrained manually, and if you don't do so, you will receive timing violations. That's it about OpenLogic clock crossings. I hope that the video helps you to understand which clock crossing to use when, and that OpenLogic in general reduces the number of clock crossings you have to write on your own.